Schrödinger's time-dependent equation. The time-dependent Schrödinger equation, as per the name, implies that the electron is dependent on time. It considers the electron to be as a moving wave. Overall, the electron's quantum state varies in this condition. In general terms, when the wave function behaves as the moving wave, so the equation is often referred to time-dependent. Derivation of obtaining Schrödinger's time-dependent equation. Schrödinger gave the equation to obtain the analytical solution of the waveform. And the expression of equation was multiplying and dividing the RHS of the equation A by M, we get. Since we know that P equals mv, momentum equals mass multiplied by velocity, thus substituting this value in equation B, where E equals total energy of the system or waveform or energy operator, P equals momentum of the system, momentum operator, U equals potential energy of the system. We have derived the values of both energy and momentum operator in our previous video, and the value obtained for energy operator E equals momentum operator P equals. Here we can see that the energy operator is time dependent and momentum operator is time independent. So in Schrödinger's time-dependent equation we have to substitute the value of the time-dependent operator. That is, on substituting the value of energy operator we get. We know that value of iota squared equals -1, thus. Or, on changing the side of the RHS to LHS of equation we get. Or, taking E common we will get. Because E does not equal 0, thus taking other term of equation D is equal to 0. Or, equation E can also be written as equation F is the final expression for Schrödinger's time-dependent equation, as we can see that no time-related term is present in equation D, so the equation is totally dependent on time. Sometimes the other forms of this equation are also used, which are obtained by putting value of momentum operator in final expression of the Schrödinger's time-dependent equation, which is something like this. Physical significance of Schrödinger's wave function. We all know that the Bohr's atomic model was quite simple and it gave information about the orbital details, energy levels and quantum number of electrons. But it was unable to explain the presence of multiple orbitals and the fine spectrum arising out of them, thus Bohr's atomic model is applicable in one electron system only. On the other hand, Schrödinger wave function has multiple unique solutions representing radius, energy, amplitude, probability. Density of the electron calculated from the wave function shows multiple orbitals with unique energy and distributions in space. Schrödinger's equation could explain the presence of multiple orbitals and the fine spectrum arising out of all atoms. Thus the Schrödinger's wave function equations played a major role in quantum physics.